Why?
Human.
You've probably imagined it. Flooring the gas pedal until the world blurs. Flying so fast that everything behind you disappears, streaking past in a smear of color. Now imagine doing that in a spaceship, faster and faster, until you're approaching the speed of light itself, roughly 670 million miles per hour. Here's the strange part. The thing that stops you isn't fuel. It isn't engineering. It isn't some distant future technology we haven't invented yet. It's the universe itself, actively fighting back against you, harder and harder the closer you get. Let's start with what actually happens to your body and your ship in the literal, measurable, already experimentally confirmed sense. Not science fiction. Physics that's been tested millions of times over in laboratories, in particle accelerators, in orbiting satellites. As your spaceship accelerates closer to light speed, your mass doesn't stay the same. It increases. Not because you're eating more space snacks, because according to Einstein's special relativity published in 1905, the faster an object moves relative to an observer, the more resistant it becomes to further acceleration. Physicists call this relativistic mass increase, and it's not a theory sitting untested on a chalkboard somewhere. Particle accelerators like the Large Hadron Collider prove it every single day, flinging protons to 99.9999991% of light speed and watching their effective mass balloon to thousands of times what it would be at rest. Engineers have to account for this ballooning mass constantly, or the machine simply wouldn't work as designed. It gets stranger the closer you look. This isn't a smooth, gentle increase either. It's a curve that stays nearly flat for most ordinary speeds, then suddenly, viciously steepens as you approach light speed, demanding exponentially more energy for smaller and smaller gains in velocity. Going from 90% to 99% of light speed takes vastly more energy than going from 0 to 90% in the first place. Here's the question that should be bothering you already. If your mass keeps increasing as you speed up, what happens to the energy required to push you even faster? It also increases, without limit. As you approach the speed of light, the energy needed to accelerate you even a tiny bit further approaches infinity. Not a lot of energy, infinite energy. Which means no matter how advanced your engines are, no matter how much fuel you're carrying, you cannot actually reach the speed of light if you have any mass at all. You can get agonizingly close, 99%, 99.99%. But the wall never fully arrives because it isn't really a wall. It's a mathematical asymptote, and nature does not make exceptions for how badly you want to get there. So let's say you get close anyway, 99% of light speed. What happens to you, specifically? Time stops behaving the way you expect. This is called time dilation, and it's maybe the single strangest, most well-confirmed prediction in all of physics. From your point of view, inside the ship, everything feels completely normal. Your watch ticks at 1 second per second. You breathe normally, blink normally, age normally. But to someone watching you from Earth, your clock appears to be running dramatically slower. If you traveled at 99% of light speed for what felt like 1 year to you, roughly 7 years would pass back on Earth. Physicist Joseph Haffel and astronomer Richard Keating actually demonstrated a version of this in 1971, flying atomic clocks around the world on commercial airliners and comparing them to stationary clocks afterward. The moving clocks were measurably precisely behind, matching Einstein's predictions almost exactly. Not because they were broken, because time itself had passed differently for them in a way you could read directly off the clock face. This isn't some abstract effect too small to matter either. GPS satellites orbit Earth fast enough and sit far enough from Earth's gravity that their onboard clocks drift out of sync with clocks on the ground by about 38 microseconds per day. That sounds tiny, but left uncorrected, your phone's map would be off by roughly 6 miles within a single day. Engineers build the correction directly into the satellite software, silently compensating for the fact that time itself moves at a different rate up there than it does down here. Now stretch that thought experiment further. Imagine a genuine near-light-speed voyage to a distant star and back. You could return to Earth having aged only a few years, while everyone you knew, everyone you loved, has aged decades. Possibly died of old age while you were gone. You wouldn't have traveled to the future in some magical sense. You would have simply experienced less time passing, while the rest of the universe kept moving at its normal pace. This isn't speculation dressed up as science fiction. It's a direct, unavoidable consequence of the same equations that engineers rely on every single day to keep global navigation systems accurate. The physics doesn't care whether you find it intuitive. There's a second distortion happening too, one that's honestly even harder to wrap your head around. As you approach light speed, the universe in front of you appears to physically compress. This is called length contraction. From your perspective inside the ship, the distance to your destination appears to shrink dramatically the faster you go. Space itself, from your point of view, folds in on itself in the direction of travel. Picture a 10-light-year journey to a nearby star. Sitting on Earth, that distance looks fixed and enormous. But if you were traveling at 99% of light speed, the actual distance you'd measure from inside your own ship would shrink to just over 1 light-year. Not because the star physically moved closer, because space itself contracts along your direction of motion, according to your own frame of reference. Someone back on Earth would insist the distance never changed at all. You'd both be right simultaneously, which is exactly the kind of thing that makes relativity so uncomfortable to accept the first time you hear it. Combine those two effects, time dilation and length contraction, and something remarkable falls out of the math. From your own experience, inside a ship approaching light speed, you could theoretically cross the entire observable galaxy in what feels like a single human lifetime. Not because you broke any laws of physics, because your personal experience of both time and distance would have compressed to make it possible, even while to everyone back home centuries had passed. There's a physicist named John Wheeler who liked to describe relativity's core lesson simply. Spacetime tells matter how to move, matter tells spacetime how to curve. Speed, mass, time, and distance aren't separate, independent things quietly sitting next to each other. They're deeply, mathematically entangled, and pushing hard enough on any one of them warps all the others. Which brings us to the truly uncomfortable part. Even if you somehow solve the infinite energy problem, even if some future civilization builds an engine capable of squeezing closer to light speed than anything we can currently imagine, you would still never actually arrive at the speed of light itself. Not with any mass, no matter how small. The rule isn't a technological limitation waiting for smarter engineers. It's baked into the geometry of the universe. And there's one more twist here that most people never hear about. If you did somehow reach light speed exactly, and photons themselves, particles of light, do exactly this, something bizarre happens to your experience of time. For a photon, from the photon's own reference frame, if it even makes sense to speak of one, 0 time passes between its creation and its absorption, regardless of how many light years it appears to travel from our perspective. Light emitted from a star 10 billion light years away, arriving at your eye tonight, experiences that entire 10 billion year journey as instantaneous. From light's own point of view, if such a point of view exists at all, there is no journey, there is no waiting, there is only arrival. So here's where this leaves you. Every time you look up at a star, you're not just seeing ancient light arriving from somewhere impossibly far away. You're witnessing the strange edge case of a universe where speed, time, and distance quietly trade places with each other, depending entirely on where you're standing and how fast you're moving when you look. It also means something a little humbling about the limits of human ambition. We can dream about interstellar travel, about generation ships, about wormholes and warp drives, and some of that may even become real one day in some form we can't fully picture yet. But the speed of light itself will likely never bend for us. Not because we're not clever enough, because the universe built that particular wall out of the same fabric it built time and space out of, and no amount of engineering ingenuity changes the geometry underneath it all. You started this imagining flooring the gas pedal until the world blurs. It turns out, at the actual edge of what's physically possible, the world doesn't just blur. It bends, stretches, and folds in on itself, until the very idea of fast stops meaning what you thought it meant.